Hello, in this video I'm going to be going over a modelling with differential equations problem from OCR A A-level in our current spec 2019 towards the middle of the paper, so it's not the hardest questions of this type we'll see. It set the scene. It's talked about a cylindrical tank built with water coming out the bottom here, so obviously height over time is going to be decreasing. It's given us the variables. It's saying that the height is x and that in time t seconds. The key things it's kind of two things that's going to enable us to set our equation up. But the first thing we're going to do is use this. The rate of change of the height of the water may be modelled by the assumption that it is proportional to the square root of the height of water. Now, they have said rate of change here, not rate of decrease, but I don't think we know it's decreasing. So I might be inclined to say minus dx by dt is proportional to is proportional to the square root of our variable, which is x. I suppose we don't really need the negative. We could have a positive. Because that'll come out in our value of k, because normally we would write this as, so the way I've set it up here, my k will be positive because I've already got a negative in the equation. But if I hadn't done that, I would have to use, I'd basically come up with k as negative. It doesn't really matter. It'll come to the same thing, amount to the same thing at the end. But in my example, the negative's already in my equation, so my k will be positive. So we now have what's called boundary conditions here. So here we're told, we're told two things. We won't use that yet. We're told that the rate of decrease is minus 0.0032 when x is equal to 0.64. So when x equals to 0.64, dx by dt is equal to minus 0.0032. So I can put that into my equation. I've got minus 0.0032 is equal to minus k times by the square root of 0.64. So that will give me k is equal to, the negatives, as I've mentioned, kind of cancel out here, and my k will be a positive the way I've set it up. So that's divided by 0.8, because 0.6 square root of 0.64 is 0.8, so that will come to 0.004. So that gives me my equation that dx by dt is equal to minus 0.004 square root of x. As I mentioned, I suppose it wouldn't have mattered if I've left the negative out here. I would have got a k as negative in my equation. Some people might have done it that way. Not really a right way of doing it. It amounts to the same thing, really. Okay. So part B is to solve that differential equation. Now here, this is compared to some of the things you see, this isn't going to trouble us too much, I don't think. So we're going to integrate both sides. So first of all, we're going to separate the variables. So like our square root of x is going to end up on the bottom. We're divided by the square root of x on both sides. So we kind of have 1 over the square root of x on the dx side, and dt minus 0.004 dt on the dt side with our integration sign there. Okay, so I'm now going to add this step in, which some of you might feel that you can skip. So we got that there. Now this isn't to add one to, this is just the normal power for integrating, so the normal rule for integrating that we've seen last year or maybe before. So, x to the n don't know what happened there. It's just some strange thing with my computer. I seem to think that was a love sign. But anyway, x to the n plus 1 over n plus 1. So we know that rule, we've seen it many times. We'll just using that there. So add 1 to the power is a half. Divide by a half. 1 divided by half, which is 2. You can check by differentiating. Differentiate that, you get x to the minus half. And here we've got minus 0.004 t plus c. So as I mentioned before, we can use the other kind of part of the boundary condition that when t is equal to 100, x is equal to 0.64 there. So we've got when t is equal to 100, x equals to 0.64. So we have 2 times by 100, sorry, 2 times 0.64 to the half equals to minus 0.004 times by 100 plus c. So that gives us c is equal to, this is 0.8, so 2 times 0.8 plus 0.4, and I think that's going to come to 2. Yes, it'll come to 2, won't it? So that's equal to 2. So we can then put that into our equation. 2x to the half is equal to minus 0.004 t plus 2. We could divide by 2, so that gives me x to the half, because it does want is equal to minus 0.002 t plus 1. So that gives us x is equal to the square of those. Let's reverse it around as well. Okay, so pretty straightforward integrating bit there. And they're going to get us to interpret that a little bit for part C. Just make a bit more space here. Incidentally, for some of you, if you're looking at the mark scheme at this and wondering why it looks a bit different, the mark scheme had t and x on the other side. So in other words, they put the constant that side. It doesn't matter. And their constant works out in -2 in the mark scheme. So it makes no difference where you put your constant left-hand side, right-hand side, t on the left-hand side or x on the right-hand side. It doesn't matter. It all comes out in the end, so long as we're consistent. So if you're wondering why c is -2 in there rather than 2, that's what's going on. Anyway, so part C, well, I think this isn't the hardest interpretation question you'll see. It says, hence determine at the time, according to the model, when the tank is empty. So it's empty when x equals 0, which gives us 1 minus 0.002 t equals 0, which gives us t is equal to 1 over 0.002, which gives us t is equal to 500 seconds. It will be empty in. So that is it. They did the mark scheme wanted the units, I've noticed. So it's interesting that they did want the units for the final A1. Often can be a bit sloppy with this, but with these kind of practical questions, they do seem to want them. Okay, that's it. I hope you found it useful. There will be one more video to come in this series. Okay, thanks, bye.